All right, so last time we started discussing one forms. So let me just remind you. Okay, one form. So this was section 1.5, one forms. What's the one form? One form is a function on the set of all tangent vectors, okay, and takes values in R. So it's tangent vectors at each point. So it is defined on this union, okay? It's a strange set, but this is what it is. So that whenever you restrict this function to any of these particular tangent spaces, so if I restrict it to the tangent space, now I know that this is a vector space. On that vector space, this function is a linear homomorphism, is a linear map. Linear homomorphism demeye gerek yok değil mi? Linear map. Homomorphism zaten linearity. A vector space homomorphism. And I guess I talk about also the following. If X this time is a vector field. Vector field means what? To each point of the space, you assign a vector space at that point. So this takes values in this union, okay? In this union. So whenever you give me a point, it gives us a vector at the tangent space to R3 at the point P, okay? So if you combine these two, okay, you have a vector field, is a vector field. Then what is the composition? Then this composition, if you first go with X and then with phi, so you start from R3. For each point, you obtain a vector at the point P, but this guy takes that vector in R at that point and gives you a real number. So the composition is a function, okay, from R3 into R. Is a function. Okay. I guess last time I gave one example about this, right? Now let me give you one more example. Şeydekiler gördüler herhalde değil mi? Şöyle yapayım. Şimdi şunu kaydedelim. Tamam. Okay. Now let me do one more example. Böyle yapınca. Okay. Example is the following. Let me talk about Okay. The okay. Example vermeyeyim de example'ı biraz sonra vereyim. Okay, let me first give a definition. Because in the example, I will need that gadget. So let me define it. If f is a differentiable function, then the differential df you know this object from advanced calculus, right? Differential of a function is a one form on R3 such that it is defined this way. This one form evaluated at a tangent vector is nothing but actually you take the vector field and feed your function to this. Okay. And we know that what this is, right? If you know the coordinates of this gadget, this is nothing but okay, let me say it this way. This is just del f del x at p v1 del f del y at p v2 plus del f del z at p v3, provided that where v is the vector with coordinates v1, v2, v3 at the point P. Okay. So this is nothing but the directional derivative of f at the point P along the vector V. Okay. So this is also the directional, hence you may think it this way also. The f evaluated at Vp is nothing but the directional derivative of f at the point P along the vector V, right? Just the dot product of the gradient with the vector. Okay. So vector fields, sorry, one forms its, okay, let's go this way. Vector fields its functions. Function gives one forms and one forms its vector fields, right? So we have such a circle. And the way we define the action of a one form, of this one form, given as for a smooth function at a vector, is just nothing but the directional derivative of f along the vector v. Okay. Sorusu olan var mı? Bakayım. Tutturabilecek miyim? Evet. Bu kadar oluyormuş. Okay. Let's do some example. Let xi from R3 to R, I from 1 up to 3 be the coordinate functions. So given by this, whenever you have a point, let's say, okay, for example, x1 is what? If your point has coordinates p1, p2, p3, this is p1. x2 of this is just p2, and x3 of p is just p3. So coordinate functions. Then so dxi at the point p at the vector vp is what? Taking okay, let vp is this vector v1, v2, v3 at the point p. So this is nothing but the directional derivative, or you know, we may think it this way. Okay, so I have the function del x1 regarded as a function, and I take derivative of this with respect to the vector, variable x1, and then I have v1. Okay, so I am using this formula at the point p, of course, v1, and then no, x1 here, x2 here, v2, plus v3. So what we get is then, okay, let's see, dx1. dx1 is just dx1 evaluated at vp is just what? Well, this derivative is 1, but these are, this is 0, and this one is 0 because x1 is independent of x2, so its derivative with respect to x2 is 0, and so on. So we just get v1. Similarly, dx2 vp is just v2, and dx3 vp is just v3. So this means what? This means, so hence since vp is just v1, v2, v3, okay, dx1, dx2, and dx3 measures measure the signed length of the projections of v to the coordinate axis. Okay, so I have this vector. Suppose I, this vector is at this point. And suppose this is the vector. Its projection onto the coordinate axis are vectors like this, right? So koordinat eksenlerine şey yaparsak, yani bu şurada bir V1, pardon, şurası, burası X1, X2, X3 olsun. So the projection of this onto this axis, let's say V2, onto this axis, it is V1, and here, let's say it is V3, okay? And this gadgets just measures those lengths, okay? Measured lengths. Why do I say measured lengths? Because these numbers can be negative, right? They don't have to be always positive. So it is not the actual length, but length with a sign. It can be both plus or minus. Therefore, we say that it is the measured length, okay? Another example. So let's say f is a function of x, y, z. So I changed the notation to x, y, z. Then what is no. I'll do another example. Okay. Okay. Hatta şurada yapayım da example'ı. Okay, let's consider okay, tornado vector field. Let's try to write down a vector field which models a tornado, okay? So it's something like this. Suppose the, the tip of the tornado, okay, it's something like this, right, is at the origin. So what kind of vector field is this? There are winds going like this, let's say, and it goes like this, and it also goes up, right? So how can we write down a vector field which, models this mathematically? Well, we know rotational vector field. It is right in the plane at the point xy. Rotational vector field is this, right? So it is, if you are at this point, then this vector is just minus y x at the point xy. Okay. But this vector field grows as you move from the origin. In this case, it should be kind of, it should be 0 here, right? There is no wind here. And then it increases, but then it decreases again. So I have to write down a function for this. And this is the origin. And let's say this is the this distance, r. R is just x squared plus y squared square root. So I guess we can write down our vector field as follows. Okay, so when r is 0, it should be 0. So let's say like this. And as you move from the origin, it gets big, but then it also, it then again goes to 0. So yeah, okay. Let's say something like this. When r is 0, it is 0. When r is positive, it is positive. But if r is very big, it becomes 0. And then let's put here okay. Oh, I see. Okay. Yeah, you're right. And then I should here put minus y x, and then a z component. Also here, let's put unit gadget. Of course, this is just a model. This is not the reality. But here again, this is proportional to r. So maybe I should write this is like r squared actually. No, this is like r. So this is r squared, another r squared. That's not good. Okay, let's make this r cubed maybe. Okay. Okay, so this is, you know, a model for this. And then, so if I take, for example, dx of x, so this vector field feed it into this one form, it gives us what? It is just the x coordinate of this, right? X coordinate of this. So it is just at a point, you know, at a particular point, this behaves like a constant. So at any point, this is just the x coordinate of this vector field. What is the x coordinate or the first coordinate? It is just r minus ry, 1 plus r cubed. Here, of course, r is just this expression, okay? So this is kind of the component of the airflow in the x direction, component of the flow at the y direction is this, rx 1 plus r cubed, and rz xp, dz xp. This is the component along the z direction. It is just r over 1 plus r cubed. R is being this expression, okay, at the point P. Here P is in point, let's say X, Y, Z. Okay. So dx, dy, dz gives us the components of the vector fields along the X, Y, and Z direction respectively, okay? Actually, you know, vector fields and one forms are dual objects, right? One of them at any point gives a vector, and the other one eats those vectors and gives us real numbers. So they are dual objects, right? If one of them forms a vector space, the other one forms are in the dual object. And you know, if you think of your linear algebra, these two vector spaces are almost the same, right? They have the same dimension and so on. So they are kind of, you know, very similar objects. And you may wonder, you know, why bother, you know, creating something similar to this and make life, you know, more complicated? The reason is that vector fields are not functorial. You know, they cannot map these using functions, but these are, you know, these are mathematically more, you know, convenient objects. These are not. Why is that? You know, suppose you have a vector field on a region like this. At each point, you have a vector like this, and you have a function, and you map this region into some other region, and then you would like to send your vector field using this f over here. The problem is the following. This function doesn't have to be one-to-one. And this means what? At this point, you have a vector. At this point, you have another vector. And both points might be mapped into a point like this. So Q is both f of P1 and f of P2. Okay. Well, you have a vector at this point and you have another vector at this point. Which one should you choose, you know, and assign to this point, right? These vectors do not have to be the same. And you don't know whether you should choose this one or this one, okay? That's why, you know, mapping vector fields under a function is not well defined, okay? So mapping vector fields under a function is not a well-defined operation. However, you can pull back one forms, okay? If you have a one form here, you can pull it back. There is no problem with that. So they behave under functions very well. However, you may, we call that operation pullback one forms. Buna push forward diyoruz. Vector pushing forward a vector field is problematic, okay? Unless your function is one-to-one, it is not well defined. But pulling one forms is always well defined, okay? So let me write it here. Pushing forward vector fields is not always well defined, but pulling back one forms are always well defined. That's why working with one forms is, advantageous. Why it is, well defined, pulling back vector one forms. You see, suppose you have a one form here. It eats vectors here, okay? You give a vector to this guy and it eats that and gives you a real number. I can pull it back over here. We call it F star phi, pull back, okay? And how it works, okay, let me tell you how it works. Bakayım. Evet, geldi. Okay. Bizim büyük silgimiz nerede? Allah, şuradaymış. So, suppose I have a function from R3 to R3, differentiable function. Okay. And we have a one form on R3. Suppose it is defined here. I want to pull it back to the other R3. How? So this is, if you want, call this U, and they don't have to be whole R3. They can be just some open sets. And I have a function here, F. And I have a one form here. I want to pull it back. So one form, R1 form, here it's vectors and gives us real numbers, right? Whenever you have a vector, let's say, this guy eats that vector and gives us a one form. Real number. And I would like to consider the pullback of this. Now, pullback of this gadget is defined this way. Suppose I have a vector here, omega at, let's say, P. Let me say this is Q. So that f of P is just Q, okay? So that f of P is equal to Q. What we do, so the value of this gadget at this vector is the following, okay. Sorry? Well, here I want to think it this way. This is defined on, I mean, you are right, but I would like to think of this way. This, one forms are defined on the vector fields, but I want to consider this open set, and whenever I take a vector field here, I'll just describe how it works, okay? So this will be what? This will be the following. I take this vector, and I push it forward by the differential of this map. So what we mean by, okay. I take the derivative map of f, differential of it, and then I obtain a vector here, let's say VP, and then I just feed it to my one form. So this is just phi of differential of f at the point P evaluated on the vector W, and then I just feed it to my one form, okay? Here df is just the derivative map, derivative of, I'm making it as a map from the tangent space, actually from R3 into tangent space at f of P to R3. The derivative map, how it is defined. DFP, you just think of, the derivative of f with respect to, okay. Yani şöyle olacak. F'in 3 tane komponenti varsa F1, F2, F3, X1, X2, X3. This is the derivative map of F evaluated at the point P. Suppose F has 3 coordinates, F1, F2, F3. Okay. So F sends points to points and sends vectors at those points to vectors at the image point, okay? And the derivative of f is just the derivative you learned in advanced calculus, okay? If f1, f2, f2 are just, f3 are the coordinates of f from, let's say, R3 into R3, you just take derivatives with respect to x1, x2, and x3 and form the derivative function. Bundan daha sonra yine bahsedeceğim. Şimdi bu kadar bahsetmiş olayım. What? df, differential of f, sends vectors to vectors. So this vector WP is sent to differential of f, which is a linear map from R3 to R3. You apply to this vector and you obtain a vector at this point, okay? Image of this tangent vector under the derivative of f. So here f goes from this open set to this open set, and differential of f goes from this tangent space to this tangent space. And it sends tangent vectors like this using its derivative. And then I take those derivative, the image of that vector and feed it to my one form. Okay. Şöyle yapayım. Şimdi şurayı sileyim. Of course, not all one forms are differentials of some functions necessarily. Here is a lemma. Any one form on R3 has the form so it's like a differential, but not necessarily differential of a function, okay? So it's something like this, 1 to 3, some functions here times dxi, where fi is just phi of ui. Ui was the frame field, okay? Where U1, U2, U3 is the standard frame field. On R3. Fi's are called the Euclidean coordinate functions of the one form phi. And let's see why this is the case. Why this lemma is important? It is important because it gives us an easy representation of one forms. Any one form is actually, point-wise, a linear combination of the three one forms, dx, dy, dz, okay? You just take some functions, multiply these functions by these one forms, coordinate one forms, and take the sum. And we claim that any one form has this form, okay? In case of functions, if you start with a function, the differential of that has this form also, where these gadgets are the partial derivatives of f with respect to dx1, dx2, dx3. But in general, these functions do not have to be differentials of a given function. They can be arbitrary functions. However, still, they have a nice representation, okay? You just consider these basic one forms and multiply them by functions and add them up. Okay. Here is the proof. well, clearly, any phi like this, fi dxi, I from 1 up to 3 is a one form. For this to be a one form, it has to satisfy two things. Whenever you have a vector, you and feed into this guy, it should give you a real number. Well, it does, because these gadgets eats vectors and gives us, right? So whenever, let's say, I have this vector at any point, v1, v2, v3, at the point P. So what is phi of Vp? Well, this is nothing but, so this expression at this is the following. So let me write it this way. dxi, v1, v2, v3 at the point P. And here, you know, I apply this gadget to this vector. This is a vector at the point P. Therefore, I compute this, you know, function at the point P. Now, these are just some real numbers. And then I have this expression. What is this? Well, this is just, what was this gadget? This just picks the ith coordinate of this. So this is just VI. So this is just I from 1 to 3, Fi evaluated at P times Vi. And I guess it is clear that, you know, this expression will be linear when restricted to any tangent space. Why is that? When you restrict it to this, when you restrict this to a tangent space, let's say TPR3, then at that tangent space, these are just fixed real numbers. And dxi's are already one forms. So what you have one forms multiplied with some real numbers, and then you sum them up. So this is nothing but, at a tangent space, this gadget is nothing but a linear combination of one forms at that point. Well, linear combination of, you know, dual vectors, they are dual vectors, is another dual vector. So I can write it this way. Moreover, at any point P, the restriction of phi to TPR3 is linear, since it is it is equal. Neye eşit bu? Şuna eşit. Yani bu nesnenin TPR3'ye restriction'ı is the sum of this real numbers f of pi and then dxi. These are just some real numbers, and you multiply those with dxi and add them up, okay? Okay. Well, I guess my time is over. Let me stop now. In the second hour, I'll prove the other part. Okay.